All right, today we're diving into the pretty amazing world of number theory to uncover a kind of hidden harmony in what at first just looks like a bunch of random numbers. So let's just jump right in. So, I want to kick things off with a little puzzle for you. I'm about to show you a set of numbers, and I promise you, at first glance, they look like they have absolutely nothing in common. But they do. Okay, here they are: 1729, 91, 111, 30, and 15. What a weird mix, right? You've got this famous number from a math story, a couple of others, and then two pretty small everyday numbers. What on earth could be the common thread here? Well, the answer, the theory that actually ties them all together, it has a name. It's called munasaba, and it is the key to unlocking this whole puzzle. So, what is munasabah? Well, at its heart, it's a theory of what you could call relational coherence. But an easier way to think about it is like this. It's a way to see a hidden web of connections. It suggests that some sets of numbers aren't random at all. They're actually linked together through all these shared and kind of beautiful properties. To actually see this web for ourselves, we're going to need a few tools. And these tools are the theory's foundation, the 6 pillars of coherence. Once we get these, we can solve our puzzle. Our journey here is going to start with some simple ideas, like repetition and prime relationships. Then we'll build up to concepts like connectors and progression. And we'll finish things off by looking at hidden cyclicity and this really powerful mathematical tool called the Mobius filter. Once we have all these, our puzzle won't stand a chance. Okay, let's start with the most intuitive one, repetition. This is all about numbers with repeated digits, like 44 or 555 or 8888. In number theory, there's a name for these. They're called rep digits. Now, what's really fascinating here is that rep digits have this hidden structure. They're always just a single digit multiplied by a rep unit, a number made up of only ones. So 111, which is in our puzzle, isn't just 3 ones. It's actually the product of 2 prime numbers, 3 and 37. So even something as simple as repetition is tied right back to the primes. So from simple repetition, we're going to dive a little deeper, right into the heart of number theory, prime relationships. This pillar focuses on a really special class of numbers called sphenic numbers. Now, the name sounds kind of complex, but the idea itself is actually super elegant. So a number is phenic if it's the product of 3 different prime numbers. That's the key. For example, 30 is 2 times 3 times 5. See? 3 unique primes. But a number like 12, which is 2 times squared times 3, it doesn't count because that prime factor 2 is repeated. It's not square-free, which is a deal breaker for being a sphenic number. Okay, so we've got these different types of numbers, but how do we link them together? Well, that brings us to our third pillar, connectors. These are numbers that act like bridges. And a fantastic example is something called a Harshad number. This is just any number that you can divide by the sum of its own digits. Let's grab 1729 from our puzzle. If you add up its digits, 1 plus 7 plus 2 plus 9, you get 19. And what do you know? 1729 is perfectly divisible by 19. And the result? It's 91. And just like that, bam, 2 numbers from our puzzle are connected. Now, beyond these direct connections, munasaba also looks for a sense of progression. This is all about the flow within a set of numbers, the way they can be ordered by increasing complexity, whether that means they have more digits or more prime factors or just more interesting properties. And a really cool example of this is the idea of Brazilian numbers. These are numbers that might not look repetitive to us in our normal base 10 system, but they are rep digits if you write them in another base. Take the number 15 from our set. In base 4, it's written as 1, 1, 1. This just adds another hidden layer of complexity and connection. Our fifth pillar helps us uncover hidden patterns through something called cyclicality. This is all about the repeating loops and patterns that numbers can fall into, and one of the simplest ways to see this is by calculating a number's digital root. To find the digital root, all you do is sum the digits of a number over and over until you get a single digit. So for 49, you get 13, and then 1 plus 3 is 4. Now for our big one, 1729, we already know the sum is 19. So we sum it again. 1 plus 9 is 10. And one last time, 1 plus 0 is 1. So the digital root of 1729 is 1. It reveals this hidden cyclical quality. And that brings us to our final killer. This is the one that gives this whole theory its real mathematical backbone. It's the Mobius function. And you can think of it as a rigorous filter that grounds munasaba in formal, serious number theory. So how does this filter work? Well, remember those sphenic numbers we talked about? The product of three different primes? The Mobius function gives any sphenic number a very specific value, -1. It's kind of like a mathematical stamp of approval. If a number gets that -1 stamp, it's confirmed to have that unique square-free prime structure. It's a way of rigorously proving that a number belongs to the sphenic club. All right, we have our 6 pillars, we've gathered our tools. It's time to go back to our puzzle and watch all the connections just fall into place.
Here they are again, 1729, 91, 111, 30, and 15. They probably still look a little random, but now we've got our munasaba lens on. Now we can finally see that hidden web of relational coherence.
Let's start with the star of the show, 1729. This number is an incredible hub. It's a central point that connects to pretty much every single pillar we've just discussed. I mean, this number is a total nexus of connections. It's phenic, built from 3 distinct primes. It's a Harshad number, which connects it to other numbers in our set. Its digital root is 1, so it's got cyclicity. And on top of all of that, it's the famous taxicab number. The smallest number you can write is the sum of 2 cubes in 2 different ways. It's just a perfect showcase of this whole idea. And now the whole web just becomes clear. You see, 1729 connects to 91 through its Harshad property. The number 30 shares that special sphenic structure. We've got our rep digit, 111, and 15 brings in that idea of progression as a Brazilian number. It's like a domino effect of connections. Suddenly, they're not random at all. Every number has its place, linked by these pillars of munasaba. So, we've solved the puzzle, but it leaves you with a much, much bigger thought, doesn't it? If this much hidden structure, this much harmony, exists in a tiny little set of just 5 numbers, what other beautiful and intricate patterns are just out there waiting to be discovered, not just in math, but in the entire universe around us?